A strong acid is a strong electrolyte. So if we know the concentration of the acid that we add to the solution, to the water, then we'll know the concentration of the products. Because, for example, if we add, let's redo that. So, for example, if we add HCl to water, and let's say the HCl was 0.1 molar, okay, then the resulting solution is going to have H3O plus formed plus chloride ions, okay? And so this is a balanced equation, and we've got a 1-to-1 ratio of the HCl forming H3O plus in solution. And that's going to account for most of the H3O plus in the solution. We're going to talk about what may account for the rest of it in just a little bit, but if that's the only acid we have in this solution, then our H3O plus will be 0.1 molar and our chloride will also be 0.1 molar, because this basically doesn't need a reversible arrow. This is a one-way arrow because it completely dissociates in solution. Okay, a strong base is also a strong electrolyte. So we have the same situation. For example, if we put sodium hydroxide into water and we form, let's say, a 0.1 molar solution, that's what we're trying to make here, then this is a one-way arrow. We're going to form Na plus OH minus from the sodium hydroxide, and it's going to completely dissociate. So the number of moles of sodium hydroxide we put in is going to equal the number of moles of sodium ion and the number of moles of hydroxide ion that we get out, because it's a 1-to-1 ratio. Okay, practically all of the hydroxide is going to dissociate. But a weak acid is a weak electrolyte. We have that two-way arrow. So if we have something, for example, like HF, hydrofluoric acid, is a weak acid. And if you put that in water, it doesn't completely dissociate. We have this two-way arrow here where we have H3O plus F minus, and so we need to do something else to account for the concentration. We're going to talk about what that thing is. We have to account for the amount of H3O plus that actually forms, because that's the way we're going to calculate what we call the pH of our solution. That's how we're going to measure how acidic our solution is. And we'll see that we have the same situation with a weak base. We have to account for the lack of complete ionization in our calculations. So here we see an example. We have H3O plus, we have HCl in water forming H3O plus, and the concentration of our H3O plus is equal to the concentration of our HCl that we originally put in. We put brackets around the concentration, and that means that's indicating that we're talking about concentration. Those brackets mean concentration, and that concentration is going to be, unless otherwise specified, in molarity, moles per liter. So when we put HCl in water, it completely dissociates, and so we can just assume the concentration that we put in is the concentration that we have, or the number of moles we put in, or the number of moles of H3O plus or acid that we have when we put it in water. So here's some strong acids: HCl, HBr, HI. Notice HF is not on this list. HF is actually a weak acid. It is the only of the halo acids that is a weak acid. Here we have nitric acid, perchloric acid, and sulfuric acid. Notice, okay, and so the hydrogens that are out in front are the ones that indicate acidity, which is the only ones that we have in these cases. But notice that sulfuric acid has two hydrogens to the left. I call it out in front, okay? And that means it's diprotic. It needs to donate. It can donate two hydrogens. The first of those is a strong acid and donates completely, and that's going to be equal to the amount of sulfuric acid we put in. The second one, it doesn't go completely, and we're going to talk about how to do those calculations, how we account for a weak acid dissociation problem. So again, weak acids only donate a small fraction of their H plus ions. Most of the weak acid molecules that we have don't donate H plus to the water. They don't increase the H3O plus concentration in water. They're usually less than 1% ionized in water. And so we have to account for their dissociation in some other way. We have to calculate the concentration some other way other than just taking the original concentration that we put in. Okay, here's some examples. Hydrofluoric, that's our halo acid that's weak. Acetic acid, formic acid, sulfurous acid. Notice this is not H2SO4, this is H2SO3. Okay, and carbonic acid and phosphoric acid. Notice that carbonic and phosphoric are diprotic and triprotic. So phosphoric acid has 3 hydrogens that can be donated. Okay, and so our strengths of acids and bases. Acid strength depends on the degree of attraction of the acid anion to the H plus. How strongly are they attracted? So the stronger they're attracted, the more likely they are to be a weak acid, because they don't want to completely dissociate. They want to hang around each other. So in other words, if I consider, for example, HF, that's why HF is a weak acid, because if I put that, well, let me write it this way. If I put HF in water, it has a stronger attraction to the fluoride has a stronger attraction to the hydrogen than the other halo acids do, and therefore it doesn't want to release the hydrogen to form the H3O plus. Okay, it wants to hang on to that hydrogen, so it doesn't completely dissociate. It remains mostly associated in water. Here we demonstrate that a strong acid has a weaker attraction between the anion and the H plus than a weak acid. That weaker attraction leads to complete ionization. We could also look at it like the anion is more stable in water. Okay? And the weak acid has a stronger attraction between the anion and the H plus, means it's less stable in water. All right, and the more stable the anion, the stronger the acid, the more likely it is to release that H plus. So how do we then calculate the concentration of our H3O plus in solution? Or why do we even care? Well, we need to be able to calculate the H3O plus concentration, because that's what leads to what we call the pH. That's our measure of acidity. Our acidity is measured by the H3O plus concentration. That's the way we calculate our pH. So we need to know what that H3O plus concentration is. And we're going to calculate that concentration by determining the percent ionization, or the extent of ionization of that acid. Okay, and the extent of ionization is represented by the Ka for the reaction. So remember setting up our K for the reaction? We set up a K as products over reactants raised to their respective coefficients. Remember that? From the last chapter, products over reactants raised to their respective coefficients. Well, Ka means the K for our reaction if our reaction is an acid dissociation reaction. If our acid is dissociating in water, we can represent that with a Ka. We call that the ionization constant. So here we have an example. We have a generic example where we have the HA plus H2O yields H3O plus A minus. These are our products, right? And these are our reactants, right? And so we're going to put our products, we have the A minus concentration times the H3O plus concentration, right, over the reactants, our HA concentration. And we're going to set that equal to the K. Now, why don't we have the water represented? Why isn't the water in our K? Because it's a liquid. Remember, we don't include liquids and solids in our constants in our reaction constants, and so we leave the water out because its concentration is effectively unchanging because it is so large compared to the rest of the species that we have there. Okay, so Ka is written as products over reactants, just like any K, leaving the water out. So basically the generic form for Ka is A minus times H3O plus over HA. Okay, we need to remember that. And we can also write that as H plus times A minus over HA, because remember, H3O plus and H plus are basically the same thing. That's saying the hydronium ion concentration, the H plus ion concentration, those are interchangeable, and our Ka is our acid ionization constant. So if we know that constant, we can calculate then the H3O plus concentration, which will give us our pH. That's how we calculate pH if we just know the concentration of the HA that we put in, right? Because we've got our balanced equation, and so we know the 1-to-1 ratio, so we'll be able to calculate that. So here are some examples of some acid ionization constants, which we call Ka, okay? And we don't need these Kas for strong acids. That's why you need to be able to recognize your strong acids, because if they're strong acids, you just calculate the H3O plus concentration by the concentration of acid you initially put in. Now the pKa is the point at which the species will gain or lose a proton, and we'll talk about pKa a little bit later on. What we're primarily concerned with right now is the Ka. So here are the examples of some weak acids and their respective reactions and their structural formulas, okay? But we need the Ka value primarily from this chart because we need to be able to calculate the concentration of H3O plus at equilibrium, which we're assuming we're reaching equilibrium to do these calculations, okay? And that way we can calculate the pH. So let's work these conceptual connection problems. Consider the three generic weak acids, HA, HB, and HC. So HA is red, HB is blue, HC is green. The images shown here represent the ionization of each acid at room temperature. Which acid has the largest Ka? Largest Ka means it's dissociated more because it has more products at equilibrium. Okay, if it has more products, it's going to have more of these little white balls, which are the hydrogens, right? The H plus. So the one that has the more white balls is the blue one, okay? So we see that indicated here. Now, which of these acids is stronger? HF or HClO. So we have the Ka being of HF being 6.8 times 10 to minus 4, and the hypochlorous acid is 2.9 times 10 to minus 8. Minus 4 is larger than minus 8, right? Because we've got the 6, let's write that down, 6.8 times 10 to minus 4 is 0.00068, right? And then 10 to minus 8 is 0.0000029, right? Is that right? Let me see. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So this is 10 to minus 4, this is 10 to minus 8. You can see that 10 to minus 4 is larger than 10 to minus 8. I alluded earlier to the idea that there was some other source of hydronium ion in water, and that's because water, being amphoteric, so it acts as both an acid and a base, can form H3O plus and OH minus by interacting with just itself. So water can act as a base, remember, and an acid, remember, but if you have just pure water in solution, it wants to act as both an acid and a base, so it acts as an acid by donating a hydrogen and forming the conjugate base, hydroxide. It acts as a base by accepting a hydrogen and forming the conjugate acid, hydronium. And it does that in solution at 25 degrees C to a predictable amount, and the concentration of hydronium and hydroxide at room temperature is 10 to minus 7 molar. 1 times 10 to minus 7 meaning that the ion product of those two things, so the hydronium times the hydroxide ion concentration, is equal to a species called Kw, and Kw is 1 times 10 to minus 14. Okay, and so this concentration, this Kw has to stay constant because that is the K for this auto ionization reaction. So as the hydronium ion concentration increases, the hydroxide ion concentration must decrease so that this product stays constant. They are actually inversely proportional. So if we know one of them, we can calculate the other. So if we actually have an acid or a base in solution and we can calculate one of them, that will allow us to calculate the other of them if we need to do that. So taking this one step further, all aqueous solutions contain both hydronium and hydroxide. Neutral solutions have equal amounts of hydronium and hydroxide, and they're equal to each other, and they both have a 1 times 10 to minus 7 concentration because the product together is 1 times 10 to minus 14. Acidic solutions have a larger hydronium than hydroxide ion concentration. Okay, so the hydronium ion will be greater than 10 to minus 7 and the hydroxide will be less. Basic solutions have a larger hydroxide than hydronium, so the hydronium will be less than 1 times 10 to minus 7, hydroxide will be greater. And we're going to see these calculations in just a little bit, and hopefully this will make a bit more sense. So here we have an example. The hydronium ion concentrations of 3 solutions at room temperature are as follows. Which solution is acidic? A, B, or C? 1 times 10 to minus 3, 1 times 10 to minus 7, 1 times 10 to minus 9. So A has a higher hydronium ion concentration. It is greater than 10 to minus 7, so this one is acidic, this one is neutral, and this one is basic.